So the next part of our unit, we're going to look at some applications of the derivative stuff that we've done so far in kinematics. So that's just the study of velocity, acceleration. You've done some of this already, maybe a few of you in your physics classes. You've got some formulas that you used in your physics classes, but maybe you didn't understand where they came from. Maybe some of the calculus now will help explain that.
Yeah, like it's so weird. Denzel in our IB math class, he just uses all the physics, like
All the physics formulas to do all the math?
but like he's not an IB physics kid.
Okay.
Okay.
He just wants to use the formulas. Well, and formulas are nice that way because they, you just plug things in, but where does a formula come from and how does it get developed? That's right. So, a little bit of review. We already know what the derivative is. The derivative is an instantaneous slope. It's the slope of the tangent. It's the instantaneous rate of change, dy dx, change in y over change in x. And so a common rate of change connects velocity, displacement, and time, right? If you travel 100 kilometers in 1 hour, then your average speed is 100 kilometers per hour. Okay. Oh, man. Right, and we've looked at some examples like this, like right at the beginning of the year. I think we did some secant line stuff saying, well, average velocity is just the slope of that secant line, where you figure out what distance did I go and how long did it take me, and that'll give me my average speed. So if it takes me an hour to go 25 kilometers, well, then my average speed was 25 kilometers per hour. That's not saying that I did exactly 25 kilometers per hour the whole way. Sometimes I was probably going faster, sometimes slower, but on average, since I traveled 25 kilometers in 1 hour, then my average speed would be 25 kilometers per hour. But if I wanted to find out, if I had a graph of what was happening, right, here's my time. Here's 1 hour there. Here is distance from home. And at 1 hour, we're 25 kilometers. Well, along the way, it might have looked like this. Maybe something like that. So if I figured out my average speed, well, my average speed would be the slope of this line. From here to here, what's the slope of that line? A rise of 25, a run of 1 hour, 25 kilometers per hour. But there are some times during this that I was going slower. For example, right here, I've stopped. I'm not, for whatever reason, maybe there was a stop sign I had to come to a stop. Usually a good idea. Okay?
We don't do that here.
Another one here. But the interesting thing is, in my distance, I stopped at this stop sign, decided to back up and stop again, and then really go through that stop sign fast so no one would notice. Maybe that's what happened. Or maybe the road was curved coming back towards my house.
And I was like, oh no, and then when he backed up, and you finally went.
Yeah. Yeah, maybe the stop sign was here. I realized, oops. So then I backed up, stopped where I was supposed to, and then took off. And then here, like,
That's 25 kilometers.
if we would do the tangent at that point, that's a super steep slope. I don't know how steep that is. Maybe I'm going 150 kilometers per hour at that point. That's probably not too smart either. But on average, I was going safely 25 kilometers per hour. So we've got an instantaneous velocity, and that would be your derivative at that point. And that would show me exactly what my speedometer was saying at that moment, right? at this moment right here where that traffic camera goes. I hate those flashes. Right, and that's your instantaneous velocity. And that's your first derivative of whatever your displacement equation is. So what do I mean by displacement equation? Well, that's what I've done right here. I've created this green graph would be a displacement equation because I've got distance here, or displacement here, and time here. Some things about speed and velocity. Velocity is a vector, it has a direction, and speed is just the speed that you're going. So mathematically, speed becomes the absolute value of your velocity. So depending on your direction, if I'm just going in two directions, I could say this direction I'm going in a positive velocity, this one would be a negative velocity to show that I'm going in the opposite direction. But for speed, it doesn't matter which direction you're going, you're just saying how fast you're going with respect to time. It's just a magnitude. So here we've got an equation for displacement. I'm not sure why, but displacement often has equations with S. Displacement? Maybe? Or maybe when you say displacement, you say S twice kind of sound. One's a C, but I'm not sure. We'll go with one of those explanations. So if you wanted to find the average velocity over the interval from 1 to 3. So when you plug in 1, where are we at? Well, 1 plus 3, you'd be at 4. And when you plug in, wow, I'm having trouble making T's today. When you plug in 3, you would have 9 plus 9, you'd have a displacement at 18.
So you do the second one minus the first one.
So what have we traveled? We've traveled 14 meters in 2 seconds. Okay? So to find the average velocity is going to be 7 meters per second. Basically, you've got your 18 minus your 4 over 3 minus 1, which will give you your 7 meters per second. You've traveled 14 meters in 2 seconds, so that would be your average velocity. Now, if you want to find the actual velocity at time t, well, that's where you're going to find your derivative. Your velocity is the derivative with respect to time of your function. So if we figure out our derivative here, well, that'll just be 2t plus 3. The initial velocity, so any time in these kinematic questions often have things about initial velocity, that is when time is 0. So our initial velocity, if we go to our velocity equation, which was 2t plus 3, at t equals 0, our initial velocity is 3 meters per second. If you wanted to find the velocity after 4 seconds, you'd plug in 4 So not too bad. You don't have your paper here today? Okay. All right, a little picture of what's happening here. This is a parabola that is opening downwards. It would have a y-intercept of 122.5. So that would make sense of that the stone is 122.5, in this case, meters above the ground. It is thrown off of the cliff, and because of gravity, falls down. Now, something is going to happen in this question that maybe you haven't noticed, especially when you did your grade 11 questions, but let's look at this. Stone's velocity after 2 seconds. Now, when we take the derivative, we get the derivative of the velocity, which is the derivative of the height, as negative 9.8. End of that row. Negative 9.8 times t. So if you plug in 2, because it's after 2 seconds, it's going to be going negative 19.6 meters per second. And that negative means that it's going in the downwards direction. Now, the negative 9.8, where have you seen that number before? That's gravity. So one of the things you might not have noticed in all of your real-life parabola questions from grade 11 is often they had a negative 5t squared or a negative 4.9t squared. Because every time you take a derivative, you're going to get that negative 9.8. And if we took the derivative again, because the derivative of velocity is acceleration, you're going to just get negative 9.8, which is acceleration. And so it's kind of interesting to see how that appears in an equation. I think sometimes you'll get, does anybody know what gravity is in feet per second? Is it 32? It's irrelevant. That's American. We're not going to worry about that. But you'll see some American textbooks have a 16 in front of their t squared as a result. Yeah. They'll have questions like that. Feet per second instead of meters per second.
So just multiply whatever you have by 3.3, whatever we have. Right.
So the time when the stone will hit the ground, well, you plug in 0. Okay. Now the ground is at 0, and this is back in our original equation. So again, one of the things you really have to determine in these questions is which equation should I use? If I wanted to hit the ground, then I would know that my height would be 0. And so now I'm using my original equation, solving for that original equation, and it's going to hit the ground at 5 seconds. Well, at 5 seconds, we can find out how fast is that stone then traveling when it does hit the ground, right? You tell your friend at the bottom of the cliff, 102, 122.5, or what was it, 122.5 meters below you. I'm just going to throw a stone down. I'd like you to catch it, okay? So now we can find out how fast is this stone traveling when your friend attempts to catch it. Well, depends how big the stone is. If it was just a little pebble, it probably wouldn't be too bad. Wouldn't matter what size that stone is, it just wouldn't feel as good if it was a big boulder traveling at 49 meters per second. Yeah, here you go, here you go. Whoo!
I'm just gonna throw a pebble down.
Yeah. Close your eyes, open your mouth. Yeah, it's all good. All right, so already mentioned this, but the rate of change of velocity with respect to time is your acceleration. So if you do the derivative of your velocity equation, you'll get your acceleration equation. And as we talked about in that last question, if we took the derivative again, we would get a constant, negative 9.8. And we know that gravity is a constant. And we could write it as the second derivative of your displacement equation. So acceleration is the first derivative of your velocity equation. It's the second derivative of your displacement equation. This is cool. So in this example, the displacement of a particle at time t seconds in meters is given by that equation. We want to find the velocity of that particle at 1 second. So again, we would have to find our velocity equation by taking the derivative. And then at t equals 1, your velocity would be 3 minus 24 plus 45, which is 24 meters per second. Again, these word problems, if you're given units, this meters and seconds, you make sure that you write your answer with the correct units as well. Find when the particle is at rest. So what does it mean for the particle to be at rest? The velocity has to be 0. So when something is not moving, its velocity is 0. So if we know that the velocity has to be 0 and we have a velocity equation, we can plug that in. Now, always remember common factor, especially when factoring, because this is a lot easier if I factor out the 3. So at t equals 5 seconds and t equals 3 seconds, our particle will be at rest. Now, one of the questions that comes up in your textbook for these types of questions is to draw a motion diagram. And so it's probably not something you've heard of before, but all it's wanting to do is to give a person a sense of how this particle is moving. Well, it's sort of a graph. It's a little bit different than a graph. What we're going to do is we're going to put 0 here and
Words fast, very fast, slow. Stop.
okay. If we go back to our equation, at time equals 0, okay? At time equals 0, it's going to be at 7 meters. So as far as setting this up, we're going to have a chart here. Maybe I'll go up to 100 just to have a scale. It's going to be starting at t equals 0, s is equal to 7. So I'm just guessing that this is around 7. We're going to look at what happens to this object. I'm just doing a linear, it's not three-dimensional. What's going to happen with this graph is we're going to put in some important points. Those points are when things are at rest. At t equals 3 and at t equals 5, we figured out that this object was at rest. So it's traveling. How is this particle traveling? At t equals 3, what is our displacement? Time, I'm just going to label it on here because the time is, the motion diagram is going to show how this path is moving. It's just a line, and I'm going to label certain places at certain times. Okay? So this is where it's starting, at 7. Maybe I will erase the 7 here and put 7 in blue for you right there. No, these diagrams, it's in the textbook, and so I thought, well, you'll get a few questions in the exercises like this so that you're not confused completely. I'll show you what they meant by them. And it's just to give you a visual of what's happening. So at t equals 3, At t equals 3, if I plug 3 in, you get
Placed like above the axis. Why is it not placed around?
right on the axis, because it's going to loop back and forth, and so I'm going to have it travel. You'll see. Well, let's finish the question, and then we'll get a sense of where it's bothering us a little bit because we're used to two-dimensional graphs. And this isn't a two-dimensional graph. It's just a diagram to show how things are moving. Okay? So if I plug in 3 into this equation, I would get 27 minus 9 times this, 108, plus 135 plus 7. Whew. What do we get there? 34, 169, 51, 61. You good with 61? Okay. 61 meters. At t equals 5, we'll go back to that equation. We'll plug in 5. So if I plug in 5, I'm going to have 125 minus 300 plus 225 plus 7. 57. Okay. So on here, I'm going to label 61 here, 57 there. What is this path? What is this object doing? It is traveling. Oops. Want to go. It's traveling. And then at t equals 3 seconds, it comes to rest. So this point right here is when time is equal to 3 seconds. It then changes direction and comes back at rest at t equals 5 seconds right here. And then it continues on in that direction afterwards.
So that's exactly what I meant.
It's kind of like your x cubed graph, right? Like if you were to graph this x cubed graph, it looks like this, right? And if what we're doing right now is we're just imagining this particle traveling in a direction. And it's going to be traveling this way. It's going to come to rest. It's going to go back in the other direction, come to rest again, and then it's going to continue traveling. So it's sort of a two-dimensional diagram of how this particle is moving.
On the bottom, that's distance, that's displacement. Like the 0 to 100.
Is displacement. Okay?
Dude, that's so
It is weird, eh?
What's the way to stretch your mind?
It's just a way to figure out, this is where it's starting, 7 meters away from something. And at 3 seconds, it's 61 meters away from whatever that point is. Then it stops, comes to rest for a second, travels back towards the object, stops again, and changes direction again. So on this one, the key points are when it comes to rest, because that's where it's changing direction. And even if we think about our displacement graph, if you plug in 5 and 3, and you plug them into this equation, what do you notice? If you plug in something less than 3, both of those would be negative, making the whole thing positive. You're increasing, then decreasing, then increasing again, which is exactly what I sketched with the cubic graph to begin with. It's increasing, then decreasing, then increasing. Now, based on displacement, displacement is distance from a specific point. You are farther away from this point, then coming back, and then continuing on away from that point. What a displacement graph looks like, because it's linear like that, is because you're not worried about in which angle it's away from that point. You're not looking in a two-dimensional kind of space or a three-dimensional kind of space. You're just talking about how far away are you from that. So we don't know as it travels from 7 to 61 if it's traveling on a curve away from that or just a straight line away from that. But that doesn't matter in this particular case. It's just how it's traveling and how it's getting either closer or farther away from that. And this gives you a visual for how its motion is going away from that point, coming back towards it, and then leaving away from it afterwards. So, part D, what is the acceleration after 1 second? Well, we figured out our velocity equation first, 3t squared minus 24t plus 45. So remember that if we have our velocity equation, we can now take the derivative of that. dv dt is going to equal our acceleration, which is going to be 6t minus 24. At time equals 1. At time equals 1, if you plug this in, your acceleration would be negative 18 meters per second squared. The time at which the acceleration is 0, again, you could take your acceleration formula here, set it equal to 0. At 4 seconds, your acceleration will be 0. If we think of that on here, that's going to be this point right there. Your inflection point on your displacement graph is going to show where the acceleration is 0.
Because you're switching from a positive slope to negative. Except your both slopes, would both slopes exist at the time?
Well, both slopes are still going to be negative there for your derivative, but you're... All right. So here's one for you to try. Calculate the times when it's at rest, so the velocity is 0. So first we'd find our velocity equation, factor it, and you find out that at time equals 3 seconds and time equals 1 second, it is at rest. So far, so good. Find the value of s at these times. So when you plug in 3, you plug in 1, you get 5, and you get 9.
Did you plug it into the derivative? I don't think so. Oh yeah, you just do it wrong. I guess so. It works.
And then you could draw your motion diagram. At t equals 0, it's at 5. At t equals 1, it's at 9. T equals 3, it's back at 5. And so that's where it changes its directions. So the arrows on that motion diagram show which way it's going.
This isn't a safe place for me.
This class?
People talking about ending people's lives.
Oh, man. Find the acceleration at these times. So then acceleration is the derivative of velocity. At 1, it's negative 6 meters per second. At 3, it's at 6 meters per second. I can go back to the motion graph.